The fundamental design defect in the F-35 comes from the belief that a fighter plane can't turn at more than 9 Gs. In order to produce a turning force, the wings must produce sufficient lift. To produce 9 Gs of turning, the wings must produce 9 times the weight of the aircraft. For U.S. fighter planes, the design lifting weight is about 90 pounds per square foot of wing area for air-to-air combat. In order to produce 9 Gs, they must produce 810 pounds of lift. At sea level, atmospheric pressure is about 2,100 pounds per square foot. At 18,000 feet, it's a little bit over 1,000. So between 15 and 16,000 feet is about the maximum altitude you're going to achieve 810 pounds per square foot wing loading. In order to increase the turning force beyond that, the wing area must be increased, the wing loading, pounds per square foot, must be reduced. The only way to do this is to physically build a bigger wing. Building a bigger wing means either expanding the wingspan, which produces an enormous amount of weight, or expanding the wing from front to back, increasing the chord length. If you increase the chord length of the wing, you can increase the thickness of the wing. One of the design concepts is called thickness to chord ratio. The principal structural fact of an aircraft wing is the stiffness. The stiffness is the ability to resist bending. This is dependent upon the wing thickness and the distance from the wing thickness to the center of the aircraft wing, times another factor called the modulus of elasticity. If the wing is made twice as thick, the wing skin can be made half as thick, and the same stiffness will be produced. If the wing thickness is half as thick and the wing is twice as long, the wing skin weighs the same amount. Most of the weight of an aircraft wing is in fact wing skin weight. The internal framing is relatively much lighter. For an aircraft similar to an F-15, by maintaining the same wingspan, the total wing area can be increased by about 70% before you run out of places to put wing. The wing, however, will be less efficient because relatively more of the wing is closer to the edge. In order to continue the process of expanding the wing chord, increasing the thickness and decreasing the wing skin can be done down to the point where the wing skin buckles. This is known as thin-walled buckling. If necessary, the wing span can also be slightly reduced to allow for greater wing chord. When this is done, a turning force of probably 12 Gs can be achieved. This is a huge military advantage. The current air-to-air missiles are designed to shoot down 9G fighter planes. The fighter plane begins to turn, the missile comes in flying much faster. The missile is designed to turn at 12 Gs, but the turning radius is v squared divided by the turning force, the turning acceleration. That means that the missile has a much larger turning radius than the fighter plane, but it can react more quickly. If you have a 12G fighter, the fighter will turn so fast, the missile cannot intercept it. The missile will miss. The only way to increase the turning force of the missile is to increase the size of the winglets on the actual missile. This produces an increase in weight and an increase in drag. Because of the increase in drag and the increase in weight, fuel has to be reduced and the missile's range is reduced. This completely defeats the design concept of an F-35 or any stealth fighter. The idea is that they stay outside and can fire missiles in before they are seen. By reducing the range of the missiles, it has to come in where it can be seen and can be fought. A 9G fighter can't be sent up against a 12G fighter. It would be suicide. It's complicated and it's difficult. The 12G fighter is clearly military superior. The problem is it can't land. You would need actually a separate airframe, a lifting wing, for landings and takeoffs. The lifting wing would allow it to take off. There would be a boom similar to a refueling boom with 3 hinges in it that would allow it to extend and separate. It would then reconnect before landing. This would enable the plane to take off and land. It would be complicated, it would be expensive, but you can't fight a war with 9G fighters. 12G fighters would win every time. The other problem with this is, of course, the pilot. For the pilot to withstand a force of greater than 9 Gs, he would have to be in a water-filled suit. The suit would be similar to an astronaut suit with what would look like a scuba diver's hood. The pilot would put on the suit, it would be sealed, he would climb into the cockpit, it would be filled with water. What happens under G-forces is the blood is physically drained from the head and fills the legs. By having water outside the legs, it would maintain pressure on the skin, prevent the blood from draining, and the pilot can withstand more than 9 Gs. You cannot fight a war with 9G fighters. The entire Air Force is obsolete, and it has been obsolete for about 40 years. Planes of this description could have been built in 1970, and unless it is changed, the U.S. Air Force will not be capable of fighting wars.